Hello, welcome to my video on data structures. In this video, we will introduce a new data structure called linked list. Linked list is similar to the array data structure in that they both store the data elements one after another. Linked list also supports a very similar set of operations like data retrieval, insertion, and deletion. So, if we don't care about the implementations and the efficiency of the operations, we can treat them as the same type of data structure. However, linked list is implemented in a different way than array, which grants it special advantages and disadvantages. Specifically, data management operations such as insertion and deletion are easier with linked list, but data access is made less convenient. To motivate linked list, let's review a little bit of the array data structure. We know that the array data structure stores data elements in continuous memory blocks. And the biggest problem with such an implementation is that when we need to insert or delete an element, it may trigger expensive data moves. For example, say we are storing n data elements in the yellow blocks and try to insert another one, but the next memory block is already occupied. In this case, we have to move all n data elements to a new place before inserting the new one. It doesn't matter whether we move the data to a new place for a larger set of memory, or we move the data to eliminate the holes caused by deletions. We do it to ensure that the data elements are stored in continuous memory blocks. In this case, a simple solution to prevent such expensive data moves is to allow storing data elements in discontinuous memory blocks. This is exactly the intuition behind the linked list data structure. As you can see here, the data elements are scattered around the entire memory space. However, when we store the data elements in discontinuous memory blocks, we lose the information regarding their relative order. To address this issue, we will introduce an additional field to record the location of its next neighbor. We will have to do it for every data element. For example, in data element 1, we store the actual data content and the location of data element 2. And in data element 2, we store the actual data content and the location of data element 3, and so on and so forth. In this case, the data elements are actually linked by those purple pointers. This is where the name linked list comes from. As we said, the purple pointers are actually the addresses of the next data element. If the address of a memory block consists of the row number and the column number, then the figure here shows the information that is actually stored in each memory block. We are storing both the original data content and the address. For example, for data element 1, we also need to include the coordinate 6, 1 to indicate that the data element 2 can be found in row 6, column 1. In reality, an address is most likely stored in a 32-bit or 64-bit word. With the links, we can easily traverse the entire set of data or access an arbitrary element by following the links. However, while we can traverse the data forward, we cannot traverse it backward. To solve the problem, we also need to store the addresses of the previous neighbors. In this case, for each data element, we store both addresses of its previous and next neighbors. Linked lists with such bidirectional links are called doubly linked list, while the one-directional ones are called singly linked list. In this module, we will focus on the doubly linked list as it's more powerful, and we will just call it linked list when the context is clear. Now, let's see how linked lists can make data insertion and deletion easier. Suppose you want to insert a data element X between I and J. What you need to do is to find a memory block to hold X, break the old links between X and Y, and add the new links between IX and between XJ. In short, you can just break the black arrows and add the red arrows. On the other hand, if you want to delete X, what you need to do is the opposite. Break the red arrows and add the black arrows. Taken together, we can see that data insertion and deletion in linked list will only incur local pointer changes instead of affecting the other data elements. This is the major advantage of linked list compared to array. Finally, let's discuss the disadvantages of linked list compared to array. For array, because the data elements are stored continuously, we can infer the address of any data element when the address of the first data element is given. For example, when we know that item 1 is stored at address 61, we can infer that item 2 is stored at address 62, and item I is stored at address 6i. In other words, we can locate and access any data element in constant time. On the other hand, for linked list, we will need to follow the links when accessing the data element. This will take up to linear time for data access. In summary, we have introduced the linked list data structure in this video. We know linked list is similar to array in terms of ADT, but it is implemented differently. It stores the data elements in discontinuous memory blocks and links them with pointers. Such an implementation facilitates data insertion and deletion, as only local pointers need to be modified. On the other hand, it also makes data access harder as we need to hop through the links. In the next video, we will introduce more details regarding linked list operations. Thanks for watching and hope to see you next time.